Hello everyone. In this talk, I will be talking about the issue with k-means vector quantization and will be presenting to you a better approach to vector quantization for learning better quantizers than k-means. I will also talk about product quantization in the final parts of this talk. So let's see the issue with learning quantizers via k-means clustering. We saw in the previous talk that the image search loss boils down to the reconstruction error of the database points with their corresponding quantized representation by assuming that our query is isotropic, as can be seen in the view graph to the left. Suppose we have an ideal query for a database embedding EN. The query is aligned with the embedding EN. Now, for EN, we have to choose which quantizer is the best out of the two options, C1 and C2. We observe that C1 is closer to EN than C2 in terms of the Euclidean distance of the isotropic vector quantization loss. But if we consider the inner product of query with the residual errors, we see the inner product with query is greater for residual error vector En minus C2 than the vector En minus C1. Note the angle between query and the error vectors En minus C2 and En minus C1. As you can see, the angle between the query and the vector En minus C2 is greater than that for between the query and En minus C1. As a result, C1 is a better quantizer than C2 in terms of Euclidean distance and the isotropic vector quantization loss. But in terms of the mix loss and inner product, C2 is the better quantizer. Let's do further analysis and see why C2 is a better quantizer. Let's break the residual error in its components parallel to embedding En and its component perpendicular to embedding En. The parallel residual error is just the projection of the residual on the embedding En. The perpendicular error is then just the residual minus its parallel component. We observe that C2 is a better quantizer than C1 in terms of inner product, as the parallel error is lesser in choosing C2 as a quantizer than in choosing C1 as a quantizer. As a result, for a given query, it is better for our loss function to put more weightage on the parallel error than the orthogonal error. Note in the view graphs, the circles and ellipses are regions where the loss is the same. As you can see in the traditional loss, we have circles as there is equal weightage on the two components of residuals. In the anisotropic loss, we see there is more weightage on the parallel error than the orthogonal error. So as you can see, in the parallel direction, the change is more than in the orthogonal direction of the loss. Let's see how we can formulate a weighted version of our loss. The following discussion is based on this paper by Google formulating such a loss. We know that what the quantization loss with respect to some query distribution looks like. To make it aware of which inner products in our loss term are higher for a given query, we simply add a weighting term to each inner product which we calculate for loss calculation. So the weighting term's value is dependent on the value of the inner product of query with the database embedding EN. As we saw in the isotropic case, the quantization loss was independent of the norm of query. Hence, we can assume the query to be uniformly spherically distributed in d dimensions. That is, Q is uniformly distributed in the d-dimensional unit sphere. Let's see how the expectation looks like given a particular value of the inner product between query and database embedding EN. Here, T is a particular value of the inner product. The value of T is norm of database embedding EN times the cost of the angle between query and embedding EN. For this value, we get a particular value of the weight, which is now independent of the query. Hence, we can take the weight value outside the expectation. Why should the expectation exist at all? Well, we actually have a set of queries for which the inner product can take the value T. Given this, we can write our loss as an integral of the conditional expectation over all values of the inner product between query and database embedding EN. The integral is performed over the integral from interval from the minimum value of T, which given the definition is negative of the norm of the embedding database embedding EN, to the maximum value of T, which is the norm of the database embedding EN. The differential in the integral is the change in the partition of queries for which the inner product between query and database embedding EN is less than T. Let's observe what is happening in the three-dimensional case. So in this view graph, we observe that the query lies in the unit sphere and En is some vector in the 3D space. The dotted line aligned with query is the projection of the database embedding En on the query. So all query lies at the tip of all query vector. It touches the surface of the unit sphere. So all queries tips touch the surface of the unit sphere, and we have to find the expectation over all these queries. So now if you see, if we rotate the query with En as axis, we see that its circle gets stretched out on the surface of the unit sphere. This circle is the partition of all queries for which the inner product between query and En is the same, that is T. The blue region in the surface of the unit sphere plus the aforementioned circle is then that partition of all queries for which the inner product is less than or equal to T. The yellow region excluding the circle is then that partition of all queries for which the inner product is greater than T. If we now stand on the tip of embedding En and look directly towards the origin, we see that the change in partition of queries for which the inner product is less than or equal to T with respect to T is the purple region marked on the surface of the unit sphere. This change is proportional to the surface area of the circle with radius sine theta for the three-dimensional space. So you can consider the width of this surface to be very small. Now, as a generalization to d dimensions, we can state that the change is proportional to the surface area of the d-1 dimensional hypersphere with radius sine theta. This implies the change in the partition of queries for which the inner product is equals to t is proportional to the circumference of that circle with radius sine theta, or pi times radius, which is sine theta. So pi times sine theta. Now we can write this term as the product of the surface area of the unit circle and sine theta. As is evident from the view graph, if we vary the value of theta from 0 to pi, the circle which corresponds to the partition of queries for which the inner product is equal to t traces out the whole unit sphere. So from 0, it will start from the tip of En, that sphere, and then slowly, like at the tip of the sphere from which the En is protruding out. So from there, it will start. The circumference will slowly increase to a maximum value when it reaches the mid portion of the sphere. So it will achieve that circumference, the whole circumference of the unit sphere, which is pi, and then like it will go down to 0. For the d-dimensional case, we can realize this expression and say that the change is proportional to the surface area of the d-1 dimensional unit sphere times sine theta raised to the power of d-2. Hence, we can write the integral in terms of theta. The differential is then d theta scaled by sine theta raised to the power d-2. And the interval where we perform the integration is from 0 to pi. Now, let's look into the conditional expectation term in the integral. We can also break the query into a component parallel to the embedding En and a component perpendicular to the embedding En. The parallel component is just the projection of query in the direction of embedding En, and the perpendicular component is then query minus projection of the query in the direction parallel to embedding En. We write the residuals into parallel and perpendicular components with respect to embedding En. Using the properties of inner products, we can break up the inner product into sum of the inner product of the components of query and residual parallel to the embedding En, and the inner products of the components of query and residual perpendicular to the embedding En. Now we can open the squares and distribute the expectation over each component. Since the parallel component of query decreases with increase in the perpendicular component and vice versa, the expectation of the product term in the square is 0 due to symmetry. Let's calculate the expectation of the squared inner product of the parallel components of the query and residual. Note, this squared inner product is only the product of the squared norms of the parallel components of the query and residual. We now need to calculate the expectation of the squared norm of the parallel components of query. Because the expectation is not is only dependent is being performed over all possible query in the unit sphere. For a given value of t, which is the inner product between query and embedding en, this expectation comes as t squared divided by norm of embedding en squared. As q parallel is simply the projection of query on the embedding en. Now, in terms of theta, by the definition of it, t, it simplifies to cos squared theta. Now, let's now calculate the expectation of the squared inner product of the perpendicular components of the query and residual. This can be simplified to the product of the squared norm of the perpendicular component of the residual and the expectation of the squared norm of the perpendicular component of the query. Now, the perpendicular component of the query is uniformly distributed in the d-1 dimensional subspace orthogonal to the embedding en with a norm of root over 1 minus p squared by the squared norm of the embedding en. For the three-dimensional case, you can imagine the perpendicular component of query to be vectors uniformly distributed in the plane whose normal vector is aligned with the embedding en. So any vector lying in this plane is orthogonal to embedding en. Hence, the expectation is then the norm squared of the perpendicular component of the query multiplied by 1 by d-1 as the perpendicular component of the query is uniformly distributed in the d-1 dimensional subspace orthogonal to embedding en. We can write this norm in terms of theta as sine squared theta divided by d-1 given the definition of t. Hence, now we have an expression for the conditional expectation term in our integral. As we put the expression in our integral and simplify things, we observe that we get a scaling term over each of the parallel and perpendicular residual errors. So we call the scaling term on the parallel residual error as h parallel and that on the perpendicular residual error as h perpendicular. The terms can be calculated given the weight function and the norm of the embedding en via the following integrals. Given the expression, we observe that for any weight function such that Wt equals to 0 for all negative t and Wt is monotonically increasing for t greater than equals to 0, the scaling term for the parallel component of the residual error, h parallel, is greater than that for the perpendicular component of the residual error, h perpendicular. The equality constant is true if and only if Wt is constant in the interval of the max and mean values of the inner product between query and embedding en. That is, in the interval from negative norm of embedding en to the norm of the embedding en. This equality constant then converts our score-aware quantization loss to the isotropic quantization loss, which is just the Euclidean reconstruction error. For the special case where the weight function is just a threshold, so the weight function is an indicator function which is equal to 0 for all values of inner product t less than t, capital T, and 1 for all values greater than or equal to capital T. Since it's such a weight function in the quantization loss, we only consider the inner products which are above some threshold capital T. With such a weight function, we see that we get some simple expressions for our scaling factors. The interval in each of the integrals are from 0 to r cos of t divided by norm of the embedding en instead of 5. So in this interval, the weight function's value is 1. And for outside that, this interval, the weight function's value is 0. For such a weight function, we can convert the loss to a simpler form where we have a scaling term eta on only the parallel residual error and no scaling term on the perpendicular residual error. This scaling term eta is given as h parallel divided by h perpendicular. We observed that for the case where our weight function is a threshold, we can calculate eta recursively as a function of the dimension d analytically. With further analysis, we see that eta has a limit as the number of dimensions moves to infinity. For the case where the threshold is chosen to be equal to 0, eta takes the value of 1. That is, equal weightage is given on the orthogonal and parallel residuals. So you can think of it that all inner products are chosen in the loss calculation. For the case when the threshold is equal to the norm of embedding en, eta takes the value of infinity. That is, the loss only considers the parallel residual error and doesn't consider the orthogonal residual error. For the case where we constrain the norm of all database embeddings to be some constant c, That is, say we constrain the database embeddings to the unit norm as well as unit norm as well via into normalization of vectors. Our data is independent of the norm of database embeddings vectors en in this case. Hence, during the full loss calculation over all database embeddings, you can just sum all the parallel residual errors and then multiply the sum with a scaling factor of beta. We can use the same technique as we used to learn codebook vectors in k-means clustering for learning codebook vectors using the anisotropic vector quantization loss. We initialize the quantizers in our codebook as k random data points sampled from our database of embeddings. We then assign each database embedding a partition by finding the nearest code word using our anisotropic quantization loss. We then update each codebook vector for each partition by finding the optimal vector minimizing the anisotropic loss for that partition of the database. We then keep on repeating the partition assignment and codebook update steps till we observe no change in the codebook or till some maximum iteration is reached. The optimal code word in the codebook update step is found via optimizing a convex loss given as follows. This loss has a corresponding solution which is given as the following expression. When both the parallel and perpendicular scaling factors are equal to each other, we can just solve the update equation and find that the new codebook vector for a partition is just the mean of the embeddings in that partition. Hence, the update equation becomes the one for k-means clustering. Now, to use this vector quantization technique in your projects, you can use the scan Python library. It is a SOTA vector search algorithm as of now. As you will see in the paper, based on the metrics, you will see it outperforms all previous approaches to vector search. I will now present the final topic in this series, product quantization. Product quantization is a better and stronger quantization technique than vector quantization. In this technique, we first split the embedding into n subspaces with dimensionality d by n. We then quantize each of the n subspaces with n codebooks having k codebook vectors, each of dimensionality d by n. As can be seen, the quantized representation is then a concatenation of n codebook vectors, each chosen from each of the n codebooks. The quantized representation is then found by minimizing a product quantization loss, which indexes the n codebooks and finds the best combination of n code words with each code word chosen from each of the n codebooks. And this combination, and we find the combination which is closest to en in terms of the quantization loss. The dot product of embedding en with its quantized representation is given as the sum of dot products in the n subspaces. Given a query, we generate a lookup table in OKD time complexity. So we are talking about how we can perform search using product quantization. So it's because for each query, we can find the dot product with one of the code words in the n subspaces simultaneously on OD time. Now, finding the individual dot products with the n data points requires OMN time complexity, as we now have n codebooks from which we select n code words defining each embedding vector in the database. Hence, the search time complexity is OKD plus MN. The following two equations present the versions of our quantization loss and 4-hour quantization loss when we use product quantization. I hope the series of talks, this series of talks gave the viewers an overview of the state of the art in audio retrieval, both query by example and query by humming. For any queries, you can contact me via email. All the references and links will be added to the video description section. Thank you and have a good day, you all.